Jai Hind. Welcome again. And in the last lecture, we have discussed about the types of the supports and types of the beams. Now, in this lecture, we will discuss about the various types of the loads which are come on the beam. So, we have covered this types of the support, reaction of force, beams, types of the beams, types of the loading of the beams. We will take in this lecture. So, first is the concentrated load or point load. Concentrated load or point load are those loads which are acting at a point. In fact, this type of the load is not possible in the real-time application because it is not possible to apply load at a point. By definition, point does not having any dimension and area. So if we go to the strength of material area, then the stress will be equal to infinite. So there is no material till date in my knowledge, or I am not acquainted about the material which is having infinite strength. So this is only the purpose for make our analysis simpler. What is point load? I can take a simple example of a simply supported beam. So what is simply supported beam? I have already explained to you in the last lecture. This is a beam which is supported at the ends. At one end, this is a roller support. Another end, this is hinge support, and it is subjected to some load which is acting at a point B or C. I will give this point A here, B here, and C here, and this load, let it be P. This is point load because this is acting at a point, or this is concentrated load. Now we will convert it into the free body diagram. This is VA. This will be hinge. So this is VB vertical. This is HB, and this is P. Now to determine the reactions, we will use the equations of static equilibrium. Summation Fy is equals to 0. We will mention the sign convention. Upward forces will be considered positive and downward forces will be considered negative. So what it will be, VA is upward positive minus P because P is downward plus VB is equals to 0. So VA plus VB is equals to P. This is equation number 1. And now I can take this as suppose for 500 Newton for the illustrative purpose. So I can make it 500 here, 500 Newton. Now taking the moment about B, I give this is 3 meter, this is 7 meter or 3 meter, for example, equal, no problem. Then I will use another equation, summation MB is equals to 0, to take the moment about point B. So this sign in convention for the moment, anti-clockwise moment I will consider positive, and clockwise moment I will consider negative. So from this VA clockwise, that's why negative, VA multiplied by 6, then 500 anti-clockwise, that's why positive, 500 multiplied by 3 is equals to 0. So we will get VA is equals to 250 Newton, and if I put this VA Here VB is equals to 250 Newton. It is simple if it is point load. Now I come to the distributed load. Distributed loads are those loads which are distributed over a certain span of the beam. And in that case, if we want to make a moment equation, it will be difficult. We have to use some integral method or method of integration. So we will learn in this lecture how we can convert these distributed load into equivalent point loads. Before that, we will discuss what are the important or primary types of the distributed loads. So there are two types of the distributed load. Uniformly distributed load means UDL, and uniformly variable load, that is UVL. So I will discuss these. Here, uniformly distributed load means the intensity of the load throughout the span over which it is distributed remains constant. Then this is uniformly distributed load. So suppose this is a beam. This is a beam. Simply supported beam I am taking for the sake of simplicity at my part. This vertical height of these arrows indicate the height or intensity. Suppose it is 10 kilonewton per meter. Span length, for example, 10 meter. Maybe 6 meter, maybe 7 meter, whatever it is. But it is having certain span. Another way of representation of UDL. Suppose this is a beam. Same beam. So another way to represent the same type of the load. This is knife edge. This is roller over the same span. Here I will write 10 kilonewton per meter, and this is 10 meter. A, B, C, D, A, B, C, D. Now, if I want to take the moment about A, this is a span length. So it will create a problem. We will learn how it will be, but the shape you can observe. The shape of this load is rectangle. This is 10 kilonewton per meter. This is 10 meter. If a scale we have taken for the distance and the load intensity is 1, then this shape will become the square. If this distance or this intensity are not equal, then the shape will be a rectangle. Clear? So we should keep in our mind, and we should remember in UDL, the shape of the load diagram is square or rectangle. Now we move to the UVL, uniformly variable. Here this is hinge, this is roller. We can keep simple rollers there also. This is UVL. From 0 to maximum value, it varies linearly. This is 10 kilonewton per meter and it is 9. So this is A, B, C and D. So the shape is a right angle triangle. Height, this is load intensity, and this is the span length L. Here it is 9. So the area of these load diagrams will be equivalent point load. We will discuss in the next slide. So this is the uniformly distributed and uniformly variable load. Now we will try to learn how can we convert this uniformly distributed load into equivalent point loads. So uniformly equivalent point load, we need to have two things: magnitude and point of application. Point of application. Magnitude, you should remember, area of load diagram. And point of application, through the centroid of load diagram. These two things we need to have. We can convert easily these distributed loads into equivalent point loads. So first, uniformly distributed load. This is hinge. This is roller support. This is, for example, 10 kilonewton per meter, and this is 15 meter, for example, 5 meters here and 5 meters here. This is A, B, C, D. It can be drawn like this also. It will not make any difference. You may find problems in this fashion where UDL is shown like this. This is 10 kilonewton per meter, 5 meter. This is point A, point B, point C. This is 5 meter, and this is 15 meter. Now the shape is a rectangle, where this span length is 15 meter and intensity of load is 10 kilonewton per meter. So the area of this load diagram, will give you the magnitude of the equivalent point load. So this area is 10 into 15 is equals to 150 kilonewton. Where it will work, the point of application. For that purpose, you need to calculate or you need to determine the centroid of the load diagram. This is a rectangle. So the centroid of rectangle is the intersection point of the diagonals. So it will be 7.5 from C rightward, right side of the C, and 7.5 meter from point D on the left hand side. So we can draw the free body diagram. This is hinge, that's why dotted. I am repeating again and again why it is dotted. because the direction I will finalize for the hinge after my analysis. If it is positive, then the assumed directions will be perfect. Otherwise, I will change the directions. Now, C, this is point C, this is point A, and from C, 7.5 meters, it will be 150 kilonewton, 7.5 meters on this side, 5 meters on this side, 7.5 meters. This is point D, and this is BB at 5 meters. Now I will apply the equations of equilibrium. The summation fx is equals to 0, rightward positive and leftward negative. So summation fx, only HA, I have assumed it is rightward. There is no other force, that's why 0. Summation Fy is equals to 0, upward positive, downward negative. So upward VA is positive, minus 150 downward, plus VB upward is equals to 0. So VA plus VB is equals to 150. This is equation number 1. Now I will take the third equation, summation M is equals to 0, about which? About A. And sign convention, anti-clockwise moment I will consider positive, and clockwise I will consider negative. So about A, VB will try to rotate it anti-clockwise. That's why VB multiplied by 5 plus 15 plus 5 is 25. Then 150 clockwise. So 150 multiplied by 12.5 is equals to 0. So VB is equals to 150 divided by 2 is equals to 75 kilonewton. So VB is equals to 75. I can write this, I can put this value in equation number 1, and VA is equals to 150 minus 75 is equals to 75 kilonewton. So UDL problem has become simpler after converting this distributed load into the point loads. Now I will come to the uniformly variable loads. Uniformly variable load. For uniformly variable load, the magnitude or intensity changes are varying uniformly from 0 to maximum value. The shape, suppose this is 10 kilonewton per meter and this is 9 meter. So this is load diagram is a right angle triangle which is having a base of 10 kilonewton per meter and height is 9 meter from C to D. This is A, this is B, this is C, this is D. So the area of this triangle is equals to P. So what is P is equals to half into 9 into 10 is equals to 45 kilonewton. This is the magnitude. Now here it will act through the centroid, where centroid lies. The centroid lies at a distance of 6 meter, that is 2 by 3 of CD, that is right side of C at a distance of 6 meter and left side of D at a distance of 3 meter. So I can convert this like this. This is VA, this is HA, this is VB, and this is 6C, 6 meter. This is 45, this is 6, this is 3, and now distance I will take, this is 5, and this is 5. So this is 5, and this is 5. Apply the same summation. Fx is equals to 0, rightward positive, leftward negative. So HA is equals to 0. There is no horizontal force, so HA is equals to 0. Summation Fy is equals to 0, upward positive, downward negative. So I will write VB upward assumed minus 45 plus this is VA, this is VA, VB is equals to 0. So it is VA plus VB is equals to 45, equation number 1, taking moment about A. So VB multiplied by 5 and 3, 8, 6, 21. 8, 6, 14. 14 plus this is 19. VB into 19. VB into 19 minus 45 into 11 is equals to 0. There is no other force. So VB is equals to 45 into 11 divided by 19. So we have in kilonewtons. Put this value in VA in equation 1 and calculate what is VA. Here can be easily determined. So for today, this is about the types of the loads subjected to the beams and how we can convert the distributed load into point loads. And I tried to explain what is significance of conversion of these distributed load into equivalent load, because the problem becomes simpler. So thank you. And in the next lecture, we will discuss about few more interesting and engaging concepts, as well as numerical problems related to the concepts we have discussed. So thank you. Thank you very much.